In number 5, we are given an exponential growth problem. We are told that the population of a bacteria colony was observed to be 300 at noon. 7 hours later, the population was 8,000. And then, assuming exponential growth, find the population at 8 p.m. the same day. So this is going to be just 5a. We want the population at 8 p.m. So we're talking about exponential growth. We need the exponential growth model. That's y equals c e to the kt. T is time that's measured since the initial observation. K is the growth constant that we'll have to determine. And then c is the initial population. So in these exponential growth problems, the initial population will always be c. So we're told that the initial population is 300. Actually, I'm going to make a table of values. So time is t, and then y is the population at time t. So we're told at time t equals 0, the population is 300. And 7 hours later, let's say that we're going to measure time in hours, so that would be when t is 7. The population will be 8,000. And then we want the population at t equals 8, at 8 p.m. Alright, so going back to our growth model, the initial population is 300. And now we need to solve for for k. Well, this is where the second line comes in. We'll substitute in 7 for t and 8,000 for y. And now we need to solve the resulting equation for k. So, peeling things away from the left side, the first thing we need to get rid of is 300. I'm going to divide each side of this equation by 300. And I'm going to write that as 7k. Now, rather than pull out the calculator, I'm just going to reduce this. I can take out a common factor of 100, so that would be 80 over 3 is equal to e to the 7k. Alright, so next let's get rid of the e. We can take the natural logarithm of each side. When the natural log and e are in this formation, they cancel out. And so we get the natural log of 80 over 3 is equal to 7k. And now we can just divide each side by 7 or multiply by 1/7. And we get k is equal to 1/7 the natural log of 80 over 3. Now, I've already calculated this value to be approximately 0.469. The more decimal places, the more accurate, up to a point, and then probably the additional digits are going to be useless. But I think this is a good compromise. 0.469. Alright, so that tells us then that our population, given by the exponential growth model, will be 300 e to the 0.469 t. And I should actually write is approximately equal to. So we are asked for the population at time t equals 8. So let's put that in. So we need 300 times I'll get it right eventually. 300 times e to the 0.469 times 8. So I'm going to put all of that exponent in parentheses. 0.469 times 8, close the parentheses, hit enter, and we get approximately 12,780, I'll round that up to 2. 12,782.